I want to tell you a story a very long time ago and very, very far away, 1.3 billion light years away and 1.3 billion years ago, there were two black holes that had been orbiting around each other already for billions of years, but we were getting very close to the final moment when they would actually merge into one single black hole. I'm David Shoemaker, and I'm going to tell you a bit about the remarkable discovery that we've just been able to do in detecting gravitational waves and observing black holes. So here's a black hole, an artist's illustration of one, but it's better with a white background because then you can see that it's a black hole. But and it's a remarkable thing because you can't see inside a black hole. Nothing comes out, but we're going to cheat and add a little bit of information here. So first off, it's a tear in space and time. It's a place where gravity has gotten so strong that space has folded up on itself. This can happen if you have a star, it's burning its nuclear fuel. When it runs out of fuel, the heat and pressure which keeps it large disappears, and it can collapse down to a mathematical point with no volume. But the mass of that star is still there. It still can weigh 30 solar masses or something fantastic like that. Around the outside of it is an event horizon. Nothing inside the event horizon can ever get out, not even light. And so, those black holes, which became one, now we can never see again. They've disappeared for all time. Now, let me zoom forward in my story from 1.3 billion years ago to about 400 years ago, where Galileo was the first to turn this new invention, a telescope, up into the skies. And there he saw the moons of Jupiter. He had opened a new window on the universe, a new way of looking at things, which would lead to an enormous collection of surprises, as well as maybe some expected things like details on the moon. But the wonderful thing about it is that it told us an awful lot about the cosmos. We've learned so many things from not only optical astronomy, but also radio astronomy and X-ray astronomy and so forth and so on. This always seems to happen when we open up a new window on the universe. But I'm going to tell you about a different approach. First, we're going to have to talk a bit about our favorite former Swiss patent office worker, Albert Einstein, who in 1916, very neatly, just 100 years ago, had published his theory of general relativity. That was a theory on gravitation, and he was starting to analyze what some of the consequences were of his theory. And he saw that if you accelerate masses, that they should give off gravitational waves. I want to try and explain a little bit about what that means. First, though, let's look, jumping back a bit in time, to Isaac Newton. He was a scientist, perhaps of the stature of Einstein, really. And he also thought a lot about gravity, and he developed a theory of Newtonian gravity. And that theory, though, was one that was based on the notion of attraction between objects, like magnets, and didn't have any engagement with space. Space was flat. It was uninvolved in the equation. Time also. Einstein's idea was different. It was to replace this idea of an attractive force with the notion that mass bends space-time. Here's an illustration where three-dimensional space has been squashed down to two dimensions for the state of illustration. And we see there the sun. The sun's making a dimple in space-time. This is Einstein's idea. And the Earth, you can see it's got its own little dimple, and it runs around in this dimple created by the gravitation from the sun. That was Einstein's notion of how this could work. It warps space-time. It also bends everything that goes by it, for instance, light as well. And in fact, one of the first proofs that we had that Einstein's theory was on target was to see the bending of light around the sun. And just you can see the New York Times from 1919, lights all askew in the heavens, but don't worry about it. It was sort of a funny headline. I do want to mention one other thing, though. If that sun were a black hole instead, that dimple would be infinitely deep. So here we are back with our black holes again. I want to talk a bit about how we could possibly detect these waves. As the black holes spin, difficult to see in this light, there are ripples in space-time that come out, and they propagate out at the speed of light. Thank you very much. And in fact, if you put an object like a meter stick in the way of those waves, it will change length by a very, very small amount as those waves propagate out. And that's the key that we're going to use to actually see these waves. These are beautiful simulations that were made. First, though, let's talk about how much energy is given off in gravitational waves, and we're going to go back to our friend Einstein, and it's probably the only formula that you, or maybe even I, could quote from Einstein, which is E equals mc squared. He found that if you had two black holes, each one about 30 times the mass of our sun, that coalesce like that, those ripples in space-time carry away 3 suns worth of energy, an inconceivable amount, 50 times the light of all the stars in the universe for a short period of time, or about a billion years of energy consumption, not of humans, but by humans. And all of that just in a few tenths of a second. It's a huge amount of energy that's given off. The other question is, how big a signal could it make? Well, let's take our example of 2 black holes, these 30 solar masses. Right at the end, you can imagine things that are 30 times the mass of our sun going around 100 times a second. That's the speed of the blades in the blender in your kitchen. And approaching each other so closely that they eventually touch and become one. If you put that system at 1.3 billion light years away, you have a very small effect indeed. Let's look at our meter stick. I'm actually from the States, and so there's a photo of a yardstick, but still, it's about the same. So if you take that meter stick and you shrink it by a factor of 1,000,000, you get to something which is about 1/10 the diameter of a human hair. But in fact, then if you shrink that by another 1,000,000, and then that by another 1,000,000,000, then you start to get a sense of the amount of motion that you could hope to see in the ends of this meter stick as the gravitational wave goes by. And that's the measurement challenge that we have in trying to detect these gravitational waves. Let me again jump forward in our story now to only 50 years ago. There was a young faculty member by the name of Rai Weiss at MIT who was teaching a course on general relativity. He was really more of a tinkerer and really liked to build experiments that could test fundamental questions in physics. So he was keeping a couple of days ahead of his students in making up problem sets, and he had a great idea. Let's take these newfangled things called lasers, make a laser interferometer, and use that as a means to detect the gravitational waves. All the students got the problem right, but Weiss really got hung up on the idea and spent all his free time for years mapping out how you might actually build an instrument that could do that in a practical way. Let's talk a bit about the measurement technique that he suggested. So here's a simulation of a gravitational wave passing through space-time. It's going at the speed of light, and like a radio wave, it makes forces perpendicular to the direction of the propagation of the wave. But the gravitational wave is an odd beast. What it does is to squeeze space in one direction and stretch it in the other, and then do the opposite in the other direction. What we want to do is to find some way of sensing that unique signature. So let's send our electroluminescent sea creature, or whatever that thing is, down onto the plane of a table that contains a laser interferometer. And how does that thing work? We have a laser which shoots a beam into a beam splitter. It splits it into 2 arms. Let's call those arms 1 meter long. The light's reflected back from those 2 arms. It's recombined at the beam splitter, and then the light comes out and falls on a photodetector, which can turn a light signal into an electrical signal. Now, if those arms move just with the signature motion of a gravitational wave, it changes the matchup of the wave phases at the output of the interferometer. It's basically a transducer that converts gravitational waves into light intensity changes and then into electrical signals. So this was the inspiration that Weiss had for how to make the detection. We then started out on a path of trying to make an instrument that could do this. And we had a whole bunch of technical problems that we had to solve to get beyond some both fundamental and some superficial problems in the detection. And you can see that what Weiss did, he told his students to get to work to solve the homework problem. And here I am in the middle, quite a number of years ago, with a couple of other graduate students in our lab at MIT. And here's what the instrument looked like that we started out on, trying to prove these technologies. And you might even recognize the fact that we have a beam splitter in the middle and then 2 arms out on the sides, about 1 meter long for the instrument, and then a bunch of old-fashioned electronics. Well, after a number of years of research, we got to the point where we had the courage to propose to the National Science Foundation to build full-scale interferometers. Why full-scale? The longer you make those arms, the bigger the signal. If you make the arms 10 times longer instead of just 1 meter, make them 10 meters, the signal will be 10 times bigger. Well, the thing that we proposed to the National Science Foundation has 4-kilometer-long arms. Here, in fact, is one of our 2 observatories. This is the one in Washington State. We have one in Louisiana. And these 4-kilometer-long arms run down through either swamps or in the desert with the light traveling in a vacuum tube. And then scientists, engineers, technicians, and many students work on this instrument to run it, to install it, and then to interpret the data that come out of it to see if we might be able to find a gravitational wave in there. I mentioned that there was a vacuum system. We have to have that because if the light goes through an air path, we have light shimmers over a hot highway, it would be distorted. So to prevent it from being masked, we run it in a very, very good high-quality vacuum system. And because we're in the States, you have to put a cover over the beam tube so that all the hunter's pot shots that are taken won't make any holes in the vacuum system. It's also good for stopping larger things. This observatory is on a nuclear site, and they were doing a scramble, and our beam tube was not on the map. Happily, no troopers were harmed in this experiment. The airbag deployed. He was wearing a seatbelt. And we have 2 observatories. We have one in Washington State, one in Louisiana, and that's for a couple of reasons. First off, you'd want to make sure, given how small the signal is, that you see the signal in both of those interferometers. But the other thing is that you want to be able to tell from where it's coming, and if you were to hit one of the instruments before the other one, you could say about where it was. The LIGO Laboratory runs these 2. It's a collaboration of Caltech and MIT, and we're very well funded by the National Science Foundation, the US taxpayers. It's been a wonderful romance, really. What did we see with those detectors? You might think this is a black hole, but it isn't. It's just nothing. We didn't see anything with those detectors because they weren't quite sensitive enough, and we knew that that might be the case. We had very poor estimates for the rates of these signals. And so we realized we had to build a better detector, and the NSF, with its courage, did as well. Here's something that helps you understand our sensitivity. We're in this little Milky Way galaxy off to the left. It's just 100,000 light years across or so. We're some little dot out in one of the arms there. Well, our initial detector could see as far as the Virgo supercluster. That's about 100 million light years out. But we wanted to have a much more sensitive detector, and the one that I'm going to tell you about now, the Advanced Reach Detector, the Advanced LIGO detector, can reach out to more than 1 billion light years and pull in signals like the ones from this black hole that we saw. So we proposed the NSF, they accepted, we started building up the bits and pieces, and after we were ready to dismantle Initial LIGO, we started to bring in the Advanced LIGO components. We needed to develop a whole new set of state-of-the-art equipment, lasers and seismic isolation systems and mirror quality and so forth and so on. And I'm going to show you a couple of photographs of those things for the fun of it. Here, for instance, is the inside of the laser room, where you can see not only is very high cleanliness required, but some very serious eyewear as well. This is when we work inside our vacuum system in the corner station where the beam splitter is. The chambers are so large that you can actually go in there and work on them. And again, cleanliness is primordial. This is one of the objects that sensed the gravitational wave as it passed. It's a block of very, very pure fused silica, 40 kilograms in mass. Its surface is polished with subatomic precision, and that it has probably the very best mirrored surface of any mirror that we have ever made. This object, then, is mounted inside the vacuum system, hung on a suspension to isolate it from outside influences. That object saw the passage of a gravitational wave. It takes lots of computers for control systems, but then also to handle the data. We use some of the largest computing clusters in science to analyze our data. And then the control room is a pretty complicated collection of computers and computer screens. We were very pleased to see how quickly this system came together. And after only several months of tuning, we felt that we had an astrophysically interesting sensitivity to go out and look again for gravitational waves. So, my story is starting to come to a focus here. 1.3 billion years after those 2 black holes coalesced together, and about the same time multicellular life was starting on Earth, actually. 100 years after Einstein predicted gravitational waves, 50 years after Rai Weiss invented the detectors, some 20 years after the NSF, MIT, and Caltech got together and built LIGO, 10 years after Advanced LIGO got the okay, 6 months after we started doing the tuning of our detector, and only 2 days after we started our observing run with those detectors, the cosmic rendezvous was complete. On September 14th, 2015, at 5:51 EDT, the gravitational waves from that 1.3 billion year old signal arrived on the Earth and came and stretched and squeezed space. This is the signal output of our two detectors, one overlaid on top of the other, showing the characteristic wiggles of space-time as the gravitational wave passes. And it all happened in just a couple tenths of a second. This is another simulation, a really nice one actually, of the two black holes. And here we can start to see, this is a case where the black holes are making those infinitely deep pits in space-time, distorting it in the most extraordinary way. Along the bottom here, you can see that there's a wiggle. It starts out looking kind of sinusoidal. It's going to get violent toward the end, though, I warn you. And this is the signal, the gravitational wave signal that we perceived with our instrument as it came in. You can see now that space-time, as it rotates, is starting to get more and more distorted. And you can start to see some interaction between the two event horizons of the two black holes. And at a certain moment, we'll slow the movie down because things happen so quickly as space-time is warped to an incredible extreme. Those three masses of our sun are turned into gravitational waves at that instant. And then the system becomes one, wobbles a bit like jello, and then the waves go traveling out in the direction of everything, including us. The beautiful simulation. I'm going to show you one more way of looking at our signal. This is a spectrogram. This is frequency on the vertical axis and time on the horizontal. Again, it's a few tenths of a second along there. And an increase in frequency looks like a sweep up. And that's just what these signals do. I'm going to take the output of that photodetector from the Michelson interferometer I showed you and put it through the sound system here. And you're going to hear the sound of our instrument in the background, and then you're going to hear a little whoop as the gravitational wave goes by. That is the electrical signal that corresponds to those two 30 solar mass objects spinning around each other. It's going to be repeated 3 times to make it easier to hear. That was our signal. I told you we had 2 detectors, and we saw that it hit our Louisiana detector at time equals 0, and it hit the Hanford detector 7 milliseconds later. Turns out that there's 10 milliseconds of travel time between the two at the speed of gravitational waves. People used to call that the speed of light. And so that means that the signal came in at a bit of an angle to our 2 detectors, and that gives us some sense of where it was in the heavens. But I think the thing that's most remarkable to me is this. This is our signal, as you see on the top here. This is the pushing and squeezing and straining of space as time goes by. The middle trace is Einstein's formula, calculated for these 2 masses at that distance. If you take Einstein's prediction of 1916, when no one had any idea that a black hole might exist, and you subtract it from that top signal, you just get noise. His prediction was, so far as we can tell, exactly right. Just an incredible man. So, a new window on the universe from Galileo, some 400 years ago, is now being echoed in a new window on the universe with gravitational waves. It will be a way to look at the heavens with a brand new signal carrier, no longer light or infrared or X-rays. These are gravitational waves that carry the information. What kinds of things might we see? Neutron stars are masses which didn't collapse all the way down to a black hole. They're not as dense as a black hole. They're only so dense that a teaspoon of material weighs 10 million tons. So we can see those things. We can see cosmic noise from either many, many gravitational wave signals all getting jumbled together like radio static, or perhaps something from the cosmic background, a gravitational wave cosmic background, supernova. But as for all previous windows that we've opened, we think that there'll be lots of surprises. I'm really excited about those. I should mention that in addition to having our 2 instruments, which are only at 1/3 of their predicted sensitivity, still more tuning to do, we also have a sister collaboration, Virgo, in Italy, and their instrument will be coming on quite soon. We'll combine the data from the 3, and that'll let us pinpoint better in the sky and extract more science from the signal. We also will cooperate with X-ray satellites and optical telescopes, combining all these different signal channels from different kinds of detectors to make ever more complete pictures of the cosmos. So here we are. From 1.3 billion years ago, when the black holes first collapsed and multicellular life first started, a rather evolved form of human life, Albert Einstein here in the middle, about 100 years ago, made the prediction that we would be able to see gravitational waves. And I love this photograph because it looks like he knows exactly how this was going to play out. And then at the end, the detection that we were able to make just last September as those waves finally came and hit the Earth and excited our detectors and me. Thank you very much.